As your narrator for the odd-numbered chapters, I would like to take a moment and say welcome to Volume 2 of the text, and I wish you good luck this semester. In Chapter 18, we discussed the electrostatic force that exists between 2 point charges. The magnitude of this force is given by Coulomb's law, where F is equal to K, Q1, Q2 over R squared. We recognize that the form of this equation is similar to Newton's universal law of gravitation for the attractive force that exists between 2 point masses. In that case, F is equal to big G, m1, m2 over R squared. Both are inverse square laws. Both depend on a fundamental constant of nature, and both are directly proportional to the product of 2 charges or 2 masses respectively. These 2 forces share another important commonality. They are both conservative forces. Recall from Chapter 6 that if we have a conservative force, then we should be able to define a potential energy associated with it. Before we do this for the electrostatic force, let's briefly recall the important aspects of the gravitational potential energy. The figure shows a basketball of mass m falling from point A to point B. The weight of the ball, mg, is the only force acting on it, where g is the magnitude of the acceleration due to gravity. We then ask the question, how much work is done by the ball's weight in moving the ball from point A to point B? Since the force on the ball is constant and along the direction of motion, the work done is equal to the force times the displacement, or mgh sub A minus mgh sub B. Recall that the quantity mgh is referred to as the gravitational potential energy of the ball, and it represents the energy the ball has just by the virtue of its position relative to the surface of the Earth. Thus, the work done on the ball by its weight is equal to the difference in the ball's initial and final gravitational potential energy. Now let's consider an analogous case for the electrostatic force. The figure shows a positive charge located between the plates of a parallel plate capacitor, which we introduced in section 18.6. We showed that a uniform electric field exists between the plates, and it points from the positive plate to the negative plate. Because of the electric field, the positive charge experiences a force, F equals QE, in the downward direction toward the negative plate. Note that there is no gravity here, just the electrostatic force. As with the basketball, an obvious question to ask is how much work is done in moving the charge from point A to point B. But this time it's the electrostatic force that is doing the work and not the weight due to gravity. Just as in the gravitational force example with the basketball, the work done by the electrostatic force in moving the charge from point A to point B is equal to the difference in the electrostatic potential energy between points A and B. The charge has a potential energy just by its position in the electric field, and this potential energy will change when the charge changes its position in the field. Notice that the work done depends only on the initial and final positions of the charge in the field and not the path taken, which is also true for the basketball in the gravitational case and true for all conservative forces in general.